morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Zero Drift Operational Amplifiers, Architecture Overview and Design Considerations, brought to you by Tech Online, Microchip, and broadcast by Aspen Core. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green paper icon located at the bottom of your screen. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window and then click the Submit button. Please note that we'll try to get to as many questions as we can at the end of the webinar today, but if we're not able to get to your question during our Q&A session, someone will be getting back to you via email after the webinar is over. And at this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. Also, at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of your console. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now, on to the presentation. Zero Drift Operational Amplifiers, Architecture Overview and Design Considerations. Discussing today's topic is Kevin Tretter, Senior Product Marketing Manager, Mixed Signal and Linear Products, Microchip. Kevin Tretter is a Product Marketing Manager with Microchip's Mixed Signal and Linear Product Group in Chandler, Arizona. He is responsible for tactical marketing support for Microchip's analog products in North and South America, as well as strategic marketing of the precision amplifier portfolio. It's with great pleasure I now turn this special session over to Kevin to begin. Kevin?
Thank you, Chris. So this webinar will focus on zero drift amplifiers, in which we will quickly explore the architectures, but the main focus will be on actually implementing these amplifiers in a design. We will first cover some basic definitions just to ensure that we are all on the same page. We will then briefly explore the two main architectures associated with zero drift amplifiers, namely auto zero and chopper stabilized. This discussion will then lead to the advantages of these architectures relative to other amplifier types. The main focus of this webinar will be on the various design considerations, some of which are somewhat unique to the zero drift architecture and therefore require special consideration. Before we get into what a zero drift amplifier is, let's first talk about some fundamental definitions. When talking about amplifiers, input offset voltage is one of the main specifications and is defined as the voltage difference between the inverting and the non-inverting input pins of the amplifier. Now, as you may recall, for an ideal op-amp model, this voltage delta is zero, but in reality, this voltage is not zero, but ranges from microvolts to millivolts in scale. Now keep in mind that this is an error voltage, so less is always better, regardless of the application. Now, in order to be considered a precision amplifier, because we've been using that term quite a lot lately, the offset voltage must be below 1 millivolt, and this is a maximum specification at room temperature. So zero drift amplifiers obviously fall under the larger umbrella of precision amplifiers. Similar to precision amplifiers, the term zero drift is an industry standard term that refers to any architecture that continuously corrects the offset voltage of the amplifier. This continuous offset correction provides for ultra-high DC precision, including low offset drift, eliminates 1/F noise, provides superior common mode rejection, as well as power supply rejection. Microchip offers two different architectures that fall under the zero drift category, auto zero and chopper stabilized. Now, these two fundamental architectures are common throughout the industry, although they may go by other names such as auto correlating zeroing, auto zeroing, or some hybrid combination of chopping and auto zeroing. Again, regardless of the architecture, the goal of a zero drift amplifier is to provide superior DC performance. We will explore these two basic architectures next. For the auto zero architecture, I'd like to point out two modes of operation, what we refer to as normal mode, shown in the top block diagram, and auto zero mode, which is shown in the bottom block diagram. In normal mode, the input signal goes from the input pins through the null amplifier, through the main amplifier, to the output buffer. The null amp gain is extremely high, and the cap C sub H holds a voltage value to correct the null amp's offset. Therefore, if you have a very high gain and very low offset, then this provides the superior performance for the null amp. The null amp then forces the voltage on capacitor C sub FW to compensate for the offset of the main amplifier. In auto zero mode, which is shown on the bottom, C sub FW ensures that the offset of the main amplifier is as low as possible, while the null amp isn't in the signal path. The null amplifier is still tied to one of the inputs, so the null amp input will track the common mode voltage. The feedback of the null amp goes back to C sub H in a voltage feedback configuration, forcing the voltage across C sub H to create the lowest offset possible. Now the amplifier switches back and forth from these two modes about every 50 microseconds or so say 10,000 times a second, enabling extremely low offsets continuously. Similar to the auto zero architecture, the chopper stabilized amplifier has two signal paths, a high bandwidth path that is always connected to the main amplifier, and a lower bandwidth auxiliary path. The main amplifier is designed for high bandwidth that extends out to the specified gain bandwidth product of the overall amplifier. This also sets the slew rate of the overall amplifier. The input signal is also routed through the auxiliary path, which has chopper switches at both the inputs and the outputs, followed by a filter stage before being added back to the main amplifier path. Similar to the null amplifier discussed in the auto zero architecture, the auxiliary amplifier has extremely high gain, enabling it to correct offsets from millivolts all the way down to microvolts. As noted earlier, regardless of the actual internal architecture, whether it is some form of auto zero, chopper stabilized, or some combination of both, the overall goal of a zero drift amplifier is to minimize the offset error on a continuous basis. Chopping frequencies of 50 to 250 kilohertz are quite common, meaning offsets are being corrected very, very often. A lot of Microchip's higher speed zero drift devices implement a 100 kilohertz chopping clock, hence offset is corrected every 10 microseconds. This frequent correction of offset has many performance benefits. Obviously this results in low initial offset, but it also enables extremely low offset drift over both time and temperature, hence the term zero drift. This also enables other offset-related benefits, such as extremely high common mode rejection, power supply rejection, and elimination of 1/F noise, which we will discuss later. I mentioned above that no user inputs are well, I don't really mention that here, but the other advantage of zero drift amplifiers is the fact that the user does not have to do anything special in order to get the amplifier to perform to that level, meaning does not have to provide a clock or a calibration signal in order to realize the performance of the zero drift amplifier. All of this additional circuitry does have some downsides, including some possible package limitations due to the size of the actual silicon implementation, higher costs driven not only by the larger silicon but also more elaborate manufacturing test setups in order to test for this level of performance. Finally, since there are internal clocks and switches, this will affect the noise performance of these devices, which is something you don't see with a traditional operational amplifier. This slide highlights several different amplifier architecture types and how the offset voltage changes as a function of time. Now the blue line near the top represents a general purpose amplifier, meaning an amplifier that does not have any sort of offset correction circuitry. Now, as you can see, the initial offset is relatively high, and offset will continue to move over time. Next is a trimmed amplifier. I call out EEPROM trimming, but this is also true for amplifiers that use other trimming techniques, such as laser trimming at the wafer level. The initial offset is much lower due to the trimming, but this architecture will still be affected by time, same as the general purpose amplifiers. Microchip offers a somewhat unique collection of amplifiers that offer on-demand calibration, which is shown in brown. Again, these amplifiers will inherently be affected by time, but the resulting offset error can be corrected with periodic calibrations. Finally, the zero drift architecture is shown in red. Since offset is being corrected thousands of times each second, the movement of offset over time is extremely small. Similar to drift over time, these architecture types are also affected by drift over temperature to varying degrees. The drift of a typical zero drift amplifier is over 100 times better than either a general purpose amplifier or even a trim device, which is still adversely affected by changes in temperature. Finally, we compare the relative change in offset versus what I refer to as environmental conditions. Now, this can include changes in output loading, changes in the common mode input levels, changes in supply voltage. Again, we see that although the trim devices offer better initial offset performance relative to, say, a general purpose device, they're still affected by the environmental changes. Zero drift devices have the benefit of compensating to these changes due to the self-correcting nature of these devices. When discussing zero drift amplifiers, words such as ultra-high performance or superior DC performance gets thrown around a lot, but what does this actually mean? Well, this chart compares some key specifications for two devices, the MCP6401, which is a general purpose op-amp, and the MCP6V61 op-amp, which is part of the zero drift series. Both are around the same speed, operate over the same supply voltage range. However, that's where the comparison really stops. As we have seen previously, offset and offset-related errors are far superior for the zero drift architecture. As illustrated, providing maximum offsets that are over 500 times better, drift that's over 130 times better, and that's being conservative, as well as common mode and power supply rejections that are 400 to 600 times better than a general purpose amplifier. So when we talk about superior performance, this is what we are referring to. Due to advances in processing capabilities as well as silicon design, zero drift amplifiers have become not only easier to use, but also are becoming more cost effective. This has led to a wide variety of devices spanning from low power to wide bandwidth offerings. As zero drift op-amps promise to make life easier for system designers, it's no wonder they are getting increased attention from all industry segments, including automotive, medical, industrial, as well as consumer applications. Next, we will move on to discuss some design considerations when implementing these zero drift amplifiers. The first topic is input bias and input offset currents. Just as a refresher, there are two physical currents that flow at the inverting and non-inverting input pins of an amplifier, noted here as IB sub N and IB sub I. Convention dictates that flow into the device is considered positive, while current flow out of the device is considered negative. Let's take a moment to address the actual definitions of these two specifications. Input bias current is defined as the average of the currents into the two input terminals of an amplifier. Input offset current is defined as the difference between the currents into the two input terminals of the amplifier. Now let's rearrange these two equations in terms of the actual currents at the op-amp inputs. With traditional operational amplifier input structures, the inputs are closely matched in terms of bias currents, so the offset is typically very, very small and hence can be ignored in most cases, meaning that the IOS over 2 term just falls out completely. However, for more complex architectures, such as a zero drift, this is not always the case. Take the MCP6V06 zero drift amplifier from Microchip. The datasheet for this device specifies a typical bias current of +6 picoamps at room temperature, but a typical input offset current of -85 picoamps at room temperature. Unlike traditional operational amplifier input stages, these zero drift op-amps have switches at the inputs that add a current flow path through parasitic switch capacitances. It turns out that the current flows through the switches from one input pin to the other. So for the MCP 6V06, IB sub n is approximately minus 37 picoamps, and IB sub I is approximately positive 49 picoamps. This means that the non-inverting input is sourcing current, while the inverting input is sinking current. Even though the average input current is relatively small at 6 picoamps, the offset current is actually quite large. Now, as noted earlier, this is a function of the self-correcting architecture of the zero-drift amplifiers and is uniquely different from the characteristics of a traditional op-amp. Although input offset currents can typically be ignored for standard op-amps, the offset may be a factor when working with these specialty amplifiers. For high-precision applications, one of the most important specifications for an amplifier is noise. Let's start with a discussion of 1 over F noise. 1 over F, or flicker noise, is inherent to all electronics, and as the name 1 over F implies, it is inversely proportional to frequency, so becoming the dominant noise source near DC. Since 1 over F noise is a slow-moving error source, the zero-drift architecture views it as an offset error, hence the noise source gets corrected. This graph compares the typical input noise voltage density graphs of 3 different amplifier architectures: the traditional, meaning no offset correction circuitry, the auto-zero topology, and the chopper stabilized topology, which we discussed earlier. The comparison here really focuses on the difference in their relative shape rather than the absolute values. The traditional time-continuous amplifier has a familiar noise profile, consisting of 2 distinct zones. You have the flat region, which is the broadband or white noise, for which the noise density is constant over frequency, and the 1 over F noise region. However, the amplifier's total noise is always a combination of the two. The 1 over F noise continues at higher frequency, but the white noise dominates in this region. And similarly, the white noise is still present in the 1 over F noise dominated region, but that particular noise is dominated by the 1 over F. So many sensor-based applications operate with high gains, maybe 100 volts per volt or even more, and at very low frequencies, typically below 10 hertz. Consequently, the 1 over F noise is potentially the main cause of system performance restrictions. Standard methods of external high or low pass filtering to help attenuate the 1 over F noise are not very practical. So in most cases, the filtering will affect the signal as well, and the low filter frequencies requires either very, very high resistance values, leading to higher thermal noise, or large capacitor values, which are physically very, very large. A more practical solution for this dilemma is the zero-drift amplifier, which virtually eliminates the 1 over F noise, as mentioned earlier. For the auto-zero amplifier architecture, the noise curve starts at a higher noise density, but then transitions to a lower noise level. This is an artifact of the auto-zero topology, which uses a sample and hold scheme to implement the offset correction, as we explored earlier. Due to aliasing, the noise is actually folded back into the baseband, leading to an increase in the auto-zero amplifier's baseband noise level. The third noise curve shown is that of the chopper stabilized amplifier. Now, this type of amplifier features the lowest noise at low frequency among the 3 examples shown. Similarly to the auto-zero amplifier, it has no distinct 1 over F noise region. The key difference to the auto-zero amplifiers is that the low frequency noise is identical to the white or thermal noise, because there is no aliasing effect. However, the noise energy is modulated to show up around the chopping clock frequency as well as its odd harmonics. Almost all chopper stabilized amplifiers include internal low pass or notch filters that will significantly attenuate this noise. However, another noise-related characteristic of chopper stabilized amplifiers is that they do exhibit some noise peaking. In this particular example, it is around 19 kilohertz. This is due to the multipath topology and the need to compensate each section of the path while also meeting the overall amplifier design goals, such as unity gain stability and proper settling behavior. However, if the amplifier is configured with higher closed-loop gain, this part of the noise spectrum, including the peak, will be significantly attenuated due to the amplifier's gain roll-off. In summary, one of the biggest advantages of zero-drift amplifiers for use in low-frequency precision applications is the elimination of 1/F noise. Each of the zero-drift topologies discussed have unique noise characteristics that vary from the traditional amplifier model. For both the auto-zero and the chopper-stabilized amplifiers, the application should include some form of output noise filtering, something a designer will have to consider for any signal chain design, regardless of the chosen amplifier type. When it comes to low-noise amplifiers, a designer must consider a number of factors, including voltage and current noise, and how the amplifier will be used within the application. In most cases, amplifiers will tout the voltage noise specification of an amplifier when discussing noise. Although this is an important specification, it is not the only one in terms of noise. Current noise may actually be a bigger concern. Keep in mind that noise has a power spectrum, which is why the bandwidth or frequency is part of the density unit. Both of these noise specifications are specified where the white noise of the amplifier dominates, hence eliminating the effects of 1/F noise. So how does a designer actually use these noise specifications when it comes to an actual application? Let's take a look at a simple example using two actual op-amps that are available on the market today. Now this table highlights some of the key specifications for these two operational amplifiers. The two are similar in terms of offset performance, speed, and operating supply voltage. The noise specifications, on the other hand, vary considerably. Again, voltage noise is usually the first noise spec that comes to mind, hence op-amp B appears to be the better choice in terms of noise performance. But is that true for all applications? For this example, consider a simple voltage follower circuit, as shown here. For the purposes of this exercise, we will focus only on the noise associated with the amplifier and the thermal noise of the input resistance, noted here as R sub n. Recall that the thermal noise voltage of a resistor is defined as shown here, where K is Boltzmann's constant, T is temperature, R is the resistance, and B is the bandwidth. For the first case, let's set R sub n to 0. Hence, the thermal noise of the resistor is 0, and the current noise of the amplifier is also eliminated, since this current must flow through an impedance in order to cause a voltage error. In this case, the noise is dominated by the voltage noise of the amplifier, hence op-amp B is the better choice. Now let's increase the input resistance to 10 kiloohms. Now the contribution of the thermal noise of the input resistor begins to factor in, and the current noise of the amplifier must also be factored in. For this case, the two amplifiers are very similar in overall noise performance. Finally, let's increase the input resistance to 100 kiloohms. The current noise of the amplifier B now becomes the dominant noise source, resulting in much worse noise performance relative to op-amp A. This simple circuit example highlights the fact that an amplifier's voltage and current noise must be taken into consideration when analyzing the noise performance of an amplifier for a given application. This is true for all amplifiers, not just zero-drift amplifiers. However, due to the input switches associated with the zero-drift topology, the current noise can be significantly higher relative to a traditional non-corrected amplifier. For high-impedance applications, such as a pH meter or an oven oscillator, or even a thermocouple isolation circuit, using an amplifier with a low current noise is critical, as the source can quickly become the dominant noise factor. The next topic that we will explore is thermal drift and how to minimize the adverse effects. What makes drift so problematic is the fact that it cannot be easily accounted for by a one-time calibration, unlike, say, an initial offset error. Since a zero-drift amplifier is continuously correcting for offset voltage error thousands of times every second, the offset drift over both temperature as well as time is very, very low, on the order of tens of nanovolts per degree Celsius, which is orders of magnitude better than an amplifier without this correction circuitry. But to realize the performance benefits of such devices, high-precision analog designs must also pay attention to the rest of the circuitry and follow sound PCB layout techniques. When two dissimilar metals come into contact and that junction is heated, a voltage shift will occur. This is commonly known as the Seebeck effect and is the basis of how thermocouples are used to measure temperature. However, there are lots of unintended thermal junctions on a typical printed circuit board, such as components soldered to a copper pad, vias, jumpers, connectors, and so forth. Consider a typical copper trace with a surface mount resistor. The thermal junction voltage effect is roughly proportional to the difference in temperature between the ends of the resistor. Assuming a temperature gradient of 0.3 degrees Celsius across the resistor, this results in a temperature drift around 1 microvolt per degree C change, which is much higher than the drift of a typical zero-drift amplifier. Now that we understand how thermal junctions work and the errors associated with them, how can we minimize these errors? Well, the key is to understand the effects of thermal junctions on a given circuit and proper PCB layout. Let's look at a simple non-inverting gain stage and explore various layout options. In this example, the layout of the resistors are placed for ease of routing, but provide very poor cancellation of thermal-related errors, as the accuracy will be impacted by gradients in both the X and the Y direction. In this next layout example, this is better, as it removes any errors that are associated with thermal gradients in the Y direction, but is still impacted by gradients in the X direction. In this third layout example, R3 is rotated 180 degrees and is now in vertical alignment with the other two resistors. This helps to minimize the thermal junction effects in the X direction. When it comes to precision analog design, a designer must consider all aspects of the circuit, not just the integrated circuits, but the passive components and how they will interact with the environment. Now, I ran through the previous layout examples rather quickly. A more detailed analysis is included in the application note AN1258 from Microchip. As it is with most things in the world of engineering, there are trade-offs when it comes to zero-drift amplifiers. The superior precision performance of these devices also leads to a disadvantage, namely their time domain performance. Events that involve driving the amplifier into an overload condition or a fast, large-scale signal step on the amplifier's input are difficult situations for self-correcting architectures. As discussed earlier, the higher bandwidth signal path within the zero-drift amplifier is responsible for the overall speed, meaning the gain bandwidth as well as the slew rate. However, once the new value of a step response is reached, the output has to settle accurately to within the same low offset limits. And this involves the bandwidth-limited correction path, and therefore is largely a function of the chopping frequency. The use of higher clock frequencies has enabled relatively fast recovery and settling times, but still, for zero-drift amplifiers, those are typically in the tens of microseconds or sometimes even a lot higher. Overdrive recovery is a similar scenario, except that the amplifier has to first return to within its linear range of operation, which usually takes some additional time. The total overload recovery time can therefore reach into the hundreds of microseconds. With the rapid expansion of wireless capabilities in the electronics industry, the presence of electromagnetic interference, or EMI, is becoming a larger issue. Although this topic goes beyond the scope of zero-drift amplifiers specifically, it is becoming a bigger and bigger concern within precision analog design. EMI affects amplifier circuits by causing a shift in the offset voltage, which causes performance degradation. Amplifier manufacturers have taken steps to minimize the effects of these unwanted signals by implementing on-chip filters. Now, for devices that have an integrated EMI filter, Microchip includes a specification table, as illustrated here, that highlights the level of rejection at common interference frequencies. There is also a characteristics graph included in the datasheet that shows the EMI rejection ratio across frequency. The effectiveness of these on-chip filters can vary, as it is, of course, highly dependent on the design as well as the implementation. Microchip technology implements a two-stage low-pass filter for EMI rejection. Most of the other amplifier suppliers typically use a single-order filter only. So the graph highlights the performance benefits of our approach. The MCP 6V7X achieves a rejection of more than 60 dB for all frequencies above 150 MHz. For the competitor device, this level of rejection isn't accomplished until closer to 1 GHz. In summary, the goal of zero-drift amplifiers, regardless of the specific architecture employed, is to minimize offset drift, and 1/F noise. In the process, other offset-related characteristics, such as common mode and power supply rejection, are also greatly improved. Due to the unique nature of this amplifier architecture relative to more traditional amplifiers, additional attention must be paid to the implementation, including leakage currents, noise considerations, and output drive overload recovery capabilities.